So today what we're doing is 3D scans. I talked about it briefly last time, but I didn't really go over it and or what the implications of that is. So a 3D scan, implies 3D K-space. So that means that you're collecting a cube worth of spatial frequency data. And so we'll just go over like how you do a 3D scan, very commonly done in order to get better signal to noise or thinner slices. And then, so last time I talked about how when you turn a gradient on, well, you do an RF pulse to line up all the spins, the precession of the spins, and then you turn a gradient on. What it does is it wraps up, in real space, it wraps up multiple cycles of phase advance. And that's fundamental to how you essentially do a physical Fourier transform of the brain. But that way of sort of thinking about it, well, that's actually what's happening in the brain, is kind of complicated because there's all these stripes and they're in 3 dimensions and it's kind of hard to sort of visualize. And so the way people think about when you're collecting data, they think about it instead, you go over to K-space, over to spatial frequency space, and gradients move where you are in K-space. That's the simpler way. So simplify it back down to a little 2-dimensional picture. And so we'll go over how to sort of think about it that way, so sort of a more simplified way than thinking about all these complicated stripes. I go over the stripes to get a real concrete picture of what the gradients are actually doing to the spins that are spread across the brain. So 3D scans. So I mentioned it last time. So we first have, frequency encoding. And what is that? That is, you do an RF pulse and then you turn the gradient on. And then you record a bunch of points with the gradient on. So that's frequency encoding. And the idea of how it works is that you're actually sort of making these stripe patterns as opposed to this way of thinking about it that will confuse you, which is that we're changing the frequency of precession and using a Fourier transform to sort of convert frequency to position. That's confusing because you can actually do the same if you just turn the gradient on and then with the gradient off, everybody at the same frequency record a data point. It's the same as the above. So that's the same. You get the same result from that. So that means that it's not critical that there are multiple frequencies on it at the moment you're recording. That's not what's going on. The frequency, the change in frequency due to the gradient is how the change in phase occurs. And so that's important. You are changing the frequencies when you turn the gradient on. But the importance of that is that what that does is cause this change in phase. And for that purpose, there's no difference between frequency encoding and the other. So that's frequency encoding, which is basically just phase encoding. And then what's phase encoding? Well, it's just exactly the same thing in a different direction, physical direction in the scanner. So in phase encoding, what do? You turn a gradient on to one of a whole bunch of different settings. So that's what this is supposed to mean. And then after the gradient is off, you do your recording. So you do recording here after the gradient is off. And so that initially looks different than frequency encoding, but you can do the same thing with frequency encoding. Just turn the gradient off and record, and it's the same thing. So that's phase encoding. And so then what is a 3D scan? A 3D scan is just do the same thing. So they call this, second phase encode direction. And direction is the critical thing there. So second, phase encode direction. And what is that? That's just phase encoding again. So it's the same thing typically, where you just turn on yet a different gradient to a bunch of different levels and then do some recording at a later point in time. So, and we'll see that it's even possible, we'll see at the end, it's even possible to turn on the gradients all at the same time. And so you can do something that's kind of like frequency encoding, like turn all 3 gradients on at the same time and then record. That's possible too. Okay, so that was just a quick review. So let's look at what the actual pulse sequence of how we turn the gradients on when we're doing a 3-dimensional scan. And so what that looks like is we've got the RF in, so RF stim, so that's actually stimulating the spins to get all aligned, and then now we've got three gradients, and then here's the signal that's coming out, and then finally, like, here's what we're recording when we're recording. So this is RF, out, and then here's the Z gradient and the Y gradient and the X gradient, and this is record. So the scan I was just doing overnight was exactly this kind of a scan. This is a fast gradient echo scan. And how does it work? You have a low angle pulse so that we don't kill too much of the longitudinal magnetization. And if you're scanning like something like the whole head, you might not even bother to turn on a slice select pulse, because as long as, there's nothing getting in the way and you're sort of stimulating the whole head, you might as well just use a frequency non-selective pulse that's very short, because the disadvantage of trying to do something like a sync pulse is that it takes a while to sort of play that out. Whereas you can just easily turn the transmitter on for a little blip and hit all different frequencies. And if we're doing a 3D scan, we actually want to hit all different frequencies. We could select a very thick slice, like just the whole head, like one giant slice that just included the whole head. And sometimes you might want to do that, but you also might want to just hit the whole thing, because we want to sort of save time. And so in that case, if you go down to the slice select, we'll just conventionally call it the Z gradient, then you don't have to turn the gradient on if you're just going to essentially stimulate everybody. So then immediately after that goes off, then we turn on one of this whole different settings of the phase encode gradient. And so this guy is the phase encode. So that's the phase encode, and then we record. So this, I'll draw out the 2D sequence first, and then we go wind up all the spins into like 128 negative direction wraps, and then change the direction of the gradient and do a readout. Usually a little bit less strong gradient than this one, because this one you just want to quickly wrap it up to 128, and now we want to record the data. And so then, what happens from this? Well, you can sort of conventionally think like from the middle of the RF pulse, you get this big FID, which we just throw away. And then in the middle of here, that's when all the spins come back into alignment. And so that's our gradient echo. and we record, we record the whole echo. And this whole echo, corresponds to one line of spatial frequency space. And it's kind of complicated. Remember, it was causing the stripes to rotate as we turn, like this thing sort of wrapped up the stripes in to 128. This one wrapped them up to whatever, could be 10, 15 plus, plus 10 or minus 27, whatever. And then as we unwrap them, we reach the middle of the echo when there's no stripes in the x direction. And then you wrap them back up again all the way up to 128 in the other direction. And we record all those data points. So this is usually called the readout direction. So that's a gradient that's on when we're actually, like this case, frequency encode. So this is readout or, frequency encode. That's phase encode, which is just the same thing, except on a different geometrical direction in the scanner. And then how do you do a 3D scan? You just turn on the other gradient. And so when we have two of these things, the conventional meaning of having two of these things is two loops. So like this one is the inner loop. So basically what that symbol means is for every setting of this GZ gradient, for a single setting of the GZ gradient, do all the y's, and then change the Z gradient to another value, and then do all the y's again. And so that's going to be a lot of data. So what's going to happen is if you have 256 of these, and you have 256 of these, then there'll be 65,000 combinations of those. And for each of those 65,000 combinations, you'll read out 256 data points. So what'll you end up with? You end up with like 16 million data points. So that's how many data points you need for a scan. And so that's so many, we have to do this as quick as possible. And so here's the next, pulse over here. So this is, this is the TR. So TR, which could be very short. So TR, for example, 8 milliseconds. So that's more than 100 per second. So that means 100. So you're doing 100 of these RF pulses per second, and each one is recording 256 points. So the data is piling in very quickly. So if you're on the scanner, sometimes this direction is, called the partition direction, which is kind of confusing. When I first heard it, I didn't understand it at all, but it just means if, for one setting of this, for one partition, do 256 of these. And so you can sort of think of that as a chunk. So that's the partition direction or second phasing code. So it's pretty straightforward. And then the last thing we should do is put in the echo time. So here's the echo time right here to the middle of the echo. So that's T, for example, 3 milliseconds. So it could be very short, and that's 8 milliseconds, and so that's 150 of these per second, and then etc. So so this is the repeat. So here we're repeating, and there's one more thing in there we can put. We're going so fast, we kind of need to get rid of some of the magnetization, and so usually we put another thing in here, another gradient, a random gradient in here. It's called this guy's called a crusher. That's to try to get rid of some of the excess magnetization. And then we might try, the change in phase, could be like 123 degrees. That's another way of trying to sort of mess up whatever leftover signal we have here, because we don't want this, whatever signal is over here interfering with our next recording. So there's various tricks. We'll come back to those. But that's all it is. That's all it is. So basically, you just, for each one of these, do all of these. And what does do all of these means? It means collect a line of data in K-space. And so what's happening, like I said last time, what's happening in the brain is that you're essentially stamping on some kind of pattern of stripes, phase stripes onto the brain. So here's the brain, the actual brain. So there's actual brain in there. And what you're doing is there'll be some, some set of stripes like this. And what are those? Those things are indicating like where the wraps are. So where this line is where the phase of the spins wraps around from like 359 degrees to 360 degrees. So that can happen. You can have a lot of those. So that's some stripe pattern that we stamped onto the brain. And then what do? We record one data point. So that corresponds to one data point, which is, like one of these over here. So just a single data point. Just one data point. And then we leave the gradient on for another chunk, and then what will happen, the same thing will happen. It'll cause the stripes to rotate. So what's going to happen is the stripes are going to rotate around. And they'll actually rotate in in two of the axes. As you do this. And so just like in 2D we saw that you wrap up all the stripes and then they sort of rotate and then they rotate back up again. Same thing is happening here, but now it's actually happening in 3D. So that's another single data point. So every data point comes from the entire head. Another single data point. And we need a whole lot of them, like 16 million or 10 million, something like that. So everybody clear on this? So it's the same as the 2D scan, except that you just have a lot more combinations of stripe patterns, because you have to do every spacing of the stripes. Those are different spatial frequencies, but then you also need every possible orientation in 3D of the stripes across the brain. And each distinct stripe pattern is one data point. Okay, so any questions about that? Is that sort of somewhat intuitive? And what's causing the stripe patterns is just, which different gradients we have on. Okay. So why do you do this compared to just selecting a slice? Because what we started off with was we said we turn on a gradient and then we play out an RF pulse that has a narrow band of frequencies, and that just picks out a single slice, and it only excites one slice. So there's several advantages of not selecting a slice. And one of them is better signal to noise, because we're hitting the entire brain. So, each data point comes from entire brain. whereas the other one, each data point is only coming from a slice. So that's definitely helpful. But there's another reason we can do thinner slices, and they're not really slices. The scanner interface calls it a slice. So like when you go to the partition direction, it says like, I have 176 slices. You don't actually have 176 slices. You just have 176 settings of the gradient, which means like 176 stripe patterns, different stripe patterns. But when you do your inverse Fourier transform and get actual slices out of it, you can get thinner ones. And why can you get thinner ones, much thinner ones? And so the problem is, if you're doing a regular slice select, so in 2D, if you do a regular, we do a slice select, and what are the constraints on doing that? So one of the constraints are, so if we want a thin slice, what we need is a steep gradient, because we want to, so we need a steep gradient. So the steeper the gradient, the thinner the slice, the narrower across the brane of the range of frequencies is. So, but then you also want a narrow RF pulse in frequency, because that corresponds to the thinness of the slice. So if you make a narrower pulse, narrower frequency band, in narrower RF pulse, frequency band, the bandwidth basically, that will make a thinner slice. If you make a steeper gradient, that will make a thinner slice. And so if you go up to the steepest gradient you can do without stimulating the person's muscles, making the muscles twitch, and then you make the narrowest RF pulse you can make. And what's the problem with making a narrow RF pulse? Well, the problem is, if we do something in time, we'll do it the other way around. So if we want to do something, if we want to make a narrow frequency band, so if this is frequency over here, what does that correspond to when we, Fourier transform it? So this is, ft going back and forth. We know that corresponds to, like, this sinc function, sine divided by sine x divided by x, and it looks like that. But the problem is, if we want to make a narrower frequency band, so if we want a narrower frequency band, what does that correspond to? That corresponds to a wider sinc, because that's the way Fourier transforms always work. Like if you make something narrower in one domain of the Fourier transform, if you on Fourier transform it, go back to the other domain, you get something wider. And so what happens is the sinc gets much wider in order to make a narrower frequency band in time. And remember, that's what we're playing out in time. And so what's that going to do? That's going to go to this part here and spread that one out in time. And before long, this thing starts to get really long and interfere with collecting your data rapidly. And so there's a practical limit to how thin of a slice you can make. You can make like a 2 millimeter slice is pretty reasonable to make, but even by then, the slice might be getting a little sloppy because you truncated the sinc pulse, and so there's kind of a hard limit at like 2-3 millimeters. You can't really, it's hard to make a thinner slice. And so with this kind of a scan, we don't really have slices. We just are stimulating the whole entire brane. And when we reconstruct, we end up with slices. And those slices can be thinner. And so that's another, much better signal to noise, and so, easier to make thinner slices. And that's a reason why people do these 3D scans all the time. Okay, so 3D scans. We'll talk more about 3D scans, like different, this one is just called a, this one was just called a flash scan, but we'll talk about an MP-RAGE scan, which is a very common one that is done that gives us very good gray-white matter. It's a little more complicated, but this one that I described here was a 3D flash. That's the name of it. And we'll talk about other kinds of, you can make other kinds of spin echo-like scans, 3D spin echo-like scans that are now heavily used. And so we'll talk about how those work. Okay, so any final questions about 3D scans or frequency encoding, phase encoding, second phase encoding, partition direction? Sort of clear. So the K-space, and the things we're talking about now, like I said, they were kind of figured out after people already had MRI magnets. So after they kind of figured out what they were doing, afterwards. And so now what we're going to talk about is that K-space view, where now we just, instead of thinking about all those complicated stripe patterns, we'll just think about a point in K-space. Since a point in K-space corresponds to a stripe pattern distributed throughout the entire brain. And then basically the idea you have is that when you turn on a gradient, any old gradient, what the effect is to move you in K-space. So that's what a gradient does. So it moves your position in K-space. And if you turn the gradient off, where you are in K-space just stays there. So our basic rules are, so if we do an RF pulse, what does that do? That basically moves you to the center of K-space. So RF pulse, after recovery, because if you assume that we've got longitudinal magnetization after recovery to magnetization longitudinal. So we've got some z-axis, and if we do an RF pulse, then what's going to happen? The result of that is, go to center of K-space. And what is the center of K-space? That's no stripes. So what is that? Why are there no stripes? It's because the spin phase of all the different parts of the brain are all the same. They're all 0 degrees, or whatever you set the phase to, but let's just say 0 degrees. So now, say you've got some longitudinal magnetization, so some transverse magnetization. So if you do an RF pulse with, some transverse mag there. So now what's going to happen is we go like a 180, for instance, so go to conjugate point. In K-space. And so what does that mean? So basically, so the conjugate point was just basically go from KX, KY point. So go from that point to just negative KX, KY. Negative KY. And why was it called the conjugate point? It was called the conjugate point because the data at that point was supposed to have its imaginary part negative. So remember, so the idea was that if we put a negative in front of the coordinates in K-space, then we're expecting the data that is at that position to be the same as this data, but with the imaginary part with a negative. That's the conjugate part. So, for a real image, parentheses, yeah, for a real image, conjugate point data as it is distinguished from the conjugate point. So conjugate point data, same with imaginary negative. So that was a particular kind of a symmetry of K-space that makes a real image. So where is the conjugate point? So the conjugate point is basically, if we have two-dimensional, it could be more complicated with 3D K-space, but if we have two-dimensional K-space, then the conjugate point is just, say we were at, Kx equals, 22, and Ky equals 10, something like that. So and so we just take negative of both of those. So, negative 22 and negative 10, that's the conjugate point. So why are we talking about this? So we're talking about this because there's negative 22 and negative 10. So we're talking about this because if you've got some transverse magnetization in there and you do an RF pulse, that's what it's going to do to it. Because say we do like a 90 and then a 180. So that's what a 180 is going to do. It's going to flip you to the conjugate part of K-space. Okay, so that's the RF pulse. And then now what the gradient does. So this was, what the RF pulse does. And now the gradient. So what the gradient does is it just moves you. So it just, what did I write? Yeah, so K-space position set by integral of gradient. So what does that mean? We already sort of talked about this, but here's a equation directly relating it. So the actual K-space position, we'll just do it in one dimension, like say Kx position, is just equal to that guy's just the constant. It's just equal to the strength of the gradient integrated over time. So this is over the time that the gradient, we'll say that we'll integrate from 0 to time equals read time. So that's when we actually read the data out. So what's the simplest integral? It's just like a rectangle. So say our gradient looks like this. So this is the gradient. And that's time. So that's this function here. That's what the gradient looks like in time. It just comes on and goes off. And so if we integrate, and then this is the point. This is the read time, okay, when we read. So say that have that be zeros, so that I lined up with this equation. So basically integrate from 0 up to when you actually read the data, and that's going to be directly equal to the spatial frequency. And what is this gradient? Well, in this simple case, just the area. So it's just the, it's just the amount of time that the gradient was on, times the strength of the gradient. So that's just the strength. Just whatever that number is when the gradient is turned on. So basic, and so they can substitute for each other. So if you just turn the gradient on for twice as strong for half as long, you'll get to the same place in K-space. And so that's like a simple one, but it works for any old one. So if you just go haywire and just turn the gradient on like something like that, and then try to figure out where are you going to be in K-space? Well, all you got to do is just integrate, which means take that area and subtract off that area and add this area onto it. And that whole thing is going to tell you exactly what spatial frequency you'll end up at. So there's a lot of times when we draw the gradients, we draw them like little trapezoids. And why do we do that? It's because you can't instantly you can't do this with the gradients. Don't like to do that. That would take an infinite amount of power in the amplifier to go from 0 all the way up to some level. And so typically we can use the equation to calculate that. And so if you have, say, 0, 1, 2 units of time, and say this is 1 unit of gradient strength, then you can have 2 units of area under the curve. But that would be exactly equivalent to doing something like this. So if we do, 1, 0, 1, 2, 3, and go up to the same level in the middle, and then go down like that, like a little trapezoid. So you can see those two things will add up to, these two things will add up to 1 unit of area and then 2 units of area. So that's the same as that. And you commonly do that with the gradient. Instead of just slamming it on, you just sort of have a little ramp and then you leave it on a certain amount. But that would also be equivalent to, something like 0, 1, 2, 3, 4. So we could go up to the same height, but just ramp it up like that and then ramp it down. That's the same, because you could sort of see if we stuck that one over there, you'd end up with the same area as before. So that's exactly the same. And when you're going really fast, the gradients often look like that. You just turn it on a little ramp and then ramp it down, because you don't have any time to sort of leave it on at a consistent thing. But all those things, because where you get to in K-space is just the integral of the gradient strength over time. So it's gradient strength multiplied by time basically to get the area. That tells you where you end up with in K-space. So now let's just go over sort of the most. So any questions about this so far? So what we're trying to do is leave the stripes behind and just think of a point. So now we just have a point in K-space that we move around with the gradients. So now let's just go back to thinking of what's going on in K-space when we do a regular pulse sequence. So the very first thing is we've let everything relax, and so we have some good longitudinal magnetization. There's no transverse magnetization lying around, and so then we just turn on the RF pulse. And so that's the absolute simplest thing, and that will put us in the center of K-space. So RF pulse. So if we just do an RF pulse, what happens? We just go to the center of K-space. So if we have no transverse magnetization, to start with, K-space will be completely empty. And so when we turn the RF pulse on, we make a spot in K-space. We sort of create some position in K-space. And then what if we did, an RF, then frequency encode. So that's the next simplest thing. So in that case, what happens is we first go to the center of K-space, and then we turn the gradient on. And what's that going to do if we turn frequency encode, in X direction? So if we turn on that means the X gradient. And so if we do that, then what's going to happen is we'll sort of march across K-space like that. Start in the center and go across. And then hopefully record data. But you can see that we didn't record the negative part of K-space here. So what does it look like when we do, frequency encode, with pre-winder? So that means that's where we kind of wrap everybody up into negative 128 stripes. So in that case, so here's there. So in that case, what we do is draw it a little bigger this time. So in that case, we start at the center, and then we turn on the X gradient full blast, and that moves us. So what is the actual pulse sequence we're looking at here? We're looking at something, like we turn on the RF pulse, and then we do something that looks like that. So that's the X gradient. So in that case, we go all the way to the left side of K-space, and then we turn it on this way, and we go back a little bit slower that way, and then record all our data points. So now we record all the data points here. And the only reason to do that is that we've got to go, we could do it by, just going across K-space here and then going back to the center again with another RF pulse and going the opposite way. Could turn on the negative gradient and go the opposite way. But it's just efficient to go, all the way to the left side and then record one line. So that's another, typical thing that we might do. What about like a very simple spin echo? So in that case, we have to use this conjugate point in K-space idea. So what about just a simple spin echo? So in that case, what is our pulse sequence? So the pulse sequence is we first do a 90, and then we do a 180. So there's 90 spin echoes on 90 and 180. And so now it's going to be a little bit more confusing. So here's our GX. So what we often do is we go up first. And then when we do our readout, we wait the right amount of time. So remember, the echo is going to, if this is like that, this is where the echo is going to occur. And so then we do our readout over here like that. It's supposed to be symmetrical. Okay, so why does that, why is this guy up? And so if we look at what's happening over here in K-space, in this, our simplified view where the gradients just move things, and a 180 might move things in K-space, then what happens is we first do a 90, that puts us in the middle, and then we do a positive pulse, and so that moves us over here. Positive gradient moves us over to the right, positive K-space. Then we do the 180, and the 180 puts us to the conjugate point. And so what is the conjugate point? The conjugate point is take wherever we were in K-space. So we were at Kx equals 128, Ky equals 0, and just take the negative of both of those. That's the conjugate point. And so the negative of 0 is 0, negative of 128 is negative 128, so we go over to negative 128. And then we wait for the echo to put itself together, and then we turn on the gradient again, and we go back across K-space like that. And as we're going back across K-space, then we record all our data. So that's a typical spin echo. So the problem with spin echo is it's this sort of putting yourself in some other part of it instantly flips you. The 180 instantly flips you to the conjugate point. So that was a spin echo. And then how about the one that I just drew in the pulse sequence, where we had a phase encode step? And so what a phase encode step is going to look like is we do our pulse. Could do a phase encode step with a spin echo, but let's just do a gradient echo. So this is a phase encode gradient echo. So now we are going to do the phase encode step, and what we'll typically do is, so here's the phase encode direction, and then here's our readout direction from before. So what we'll typically do is turn so here's the RF pulse, don't do anything during that, and then let's turn a positive gradient on. So we turn a positive gradient on for the phase encode step, one of those multiple steps. And then at the same time, we turn a negative gradient on. And so a lot of times in the MRI, you want to go as absolutely fast as possible. And so since the gradients don't interact with they do interact, but we said that because of this wraparound, if you do a gradient in one direction, it doesn't mess up the stripes in the other direction if you're just counting in that direction. So we turn both gradients on at the same time, and then we do the readout. And so what does that look like over here? So now what's going to happen is we turn the RF pulse on. That puts us in the center. And then we turn on two gradients. And so if we turn on two gradients, it's just going to move us along a diagonal. So this y is positive, so that's going to go in the positive y direction, and then this x is negative, that's going to go in the negative x direction, so we'll do something like this. So, here's point A. That was right after the pulse right here, and now here's point B. So now we're at point B, and then we go across K-space. And so here's point C. So now we go across K-space and record all our data points as we're going across K-space. So that's a typical thing that we do. So we record one line of K-space and basically just put both gradients on at the same time, and that causes us to go sort of diagonally across K-space and record one line of data. And then for a different phasing code step, we could, maybe a negative phasing code step, we would turn on a minus y gradient, go down to here, and then record a line down here. So now the problem is we just want to be able to fill up K-space as quickly as possible. And you could immediately think, oh, there's all different things. Why don't we've still got some magnetization left here. Why don't we just go the other way? So you can do that. You can sort of like go back and forth across K-space. But you can do, more creative things. So what if we turned on both the x and the y gradient at the same time? Nothing's stopping us from doing that. So here we turned them on at the same time, and we weren't recording because we were only recording, here's where we were doing the recording over here. But why don't we just turn them on at the same time and record? There's nothing that says you can't do that. And so what would that look like? So that would look like what we call a spiral scan. So we could do a pulse, do an RF pulse, and then let's turn both gradients on at the same time. So here's GY and GX. So maybe after the pulse ends, maybe put like, something like that in one, and then put something, like that, a little offset one in the other. And while that's happening, record data. So in that case, you just turn the quote-unquote phasing code direction on, gradient on at the same time as the quote-unquote frequency encode gradient was on. Just turn them on both at the same time. And what happens, what would happen in K-space, you'd basically start at the center. Let's see which direction we're going, see if I can figure it out. So we're going positive in y and then negative in x. So basically we would go positive in y and negative in x. So we would be going this way. So basically what would happen is we would just sort of go around in a spiral like that. And then record data. So, they should record data all around here. And so what we're doing is we're very rapidly going through all of K-space to try to, and there's certain advantages to doing it that way. The gradients like to do this. So this is easy on gradients. They like to make little sine waves like that. And so because of that, they can do that much faster than they can do these very sharp edge things, like maybe 4 times faster, really fast. And so this is one way to collect data extremely fast, to do a spiral. And then, people said, why stop there? Why don't we, forget about the pulse sequence? Why don't we do something like, let's go here and let's go back and forth across K-space like that. Yeah, we could do that if we wanted. That's one way of collecting data. And then, collect data the whole time. And you could also think, well, why don't we turn all 3 gradients on at the same time? And this is my most favorite scan. So there's the volume of K-space. So this is, 3D K-space. We've been talking about 2D K-space, but if we do a 3D scan with all the gradients on, it's kind of like a spiral scan, but in 3D. So you go to the center of you do an RF and go to the center of K-space, and then you could start to go around sort of like an atom in 3D, and sort of like go to all different parts of K-space like that, and you can go super duper fast, and try to because we need to collect 16 million data points, and so you can do all different kinds of things. So trying to think of this in terms of what the stripes are doing is quite complicated, and so this is the way that people people think of it. They just think of it like, how are we going to fill all the different parts of K-space that we need in order to make it a full image. So you just sort of think in K-space instead of thinking sort of in brain space. Okay, so everybody okay on this? So this is like the K-space perspective, which I said, like people, after they had a working MRI magnet, they sort of thought of it this way afterwards. And so this is how you kind of understand these different pulse sequences, different strategies to find ways of filling up all the data in K-space. Okay, so any remaining questions? Trying to find a hole on the board where my face won't block out something. So any questions about gradients move where you are in K-space? And it's the integral over time of the gradient strength. So it's gradient strength plus how long you had it on, and that determines where you go to in K-space. And if you think of it this way, then it's not so strange to have something like spiral, where you just turn on both of the quote-unquote frequency encode and phase encode at the same time, and then record data with them both on. That's okay. There's no reason you can't do that. Okay, any questions out there? So 3D scans, there's a 3D scan down there, and gradients move you around in K-space. And you can only be in one place in K-space at a time. And so each point in K-space corresponds to one data that came from the entire brain. Any questions? So for better or for worse, I posted the second homework. Never a dull moment. So you can go and check. Woohoo! You can go and there's plenty of time to work on it. It's all about K-space. Just fiddling around in K-space, like get an image, Fourier transform it, un-Fourier transform it, Fourier transform it again, mess with it, un-Fourier transform it. So leave out a couple lines, un-Fourier transform it. It's just to get a feel for how this all works. Any questions? Final questions? Going okay? Not too bad. Going kind of fast. Okay, we'll take up again on Friday.